Swayam Prabha. Digital India. Educated India.
Welcome to the next session on Organic Chemistry Paper 3. In Unit 1, Nitrogen containing functional groups. In Lecture 7, we are going to study about Diazonium salts. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project is sponsored by DTH Swayam Prabha, MHRD, New Delhi. Let us look at the topics that will be covered in this particular session. We are going to study about diazonium salts. So, the first one will be the preparation of diazonium salts we will study. Then we will study about the various reactions of diazonium salts. We have two major categories, one in which the nitrogen is lost, another category where the nitrogen is retained. So, under the category of nitrogen is lost, we will be looking at the reactions of replacement of diazonium group by hydroxyl unit, hydrogen, halogen, cyano group, nitro group or aryl groups. These are all the various replacement reactions we will study. Some of the named reactions that we will cover include Sandmeyer reaction, Gattermann reaction, Ball-Scheelmann reaction, Gomberg reaction and Mervin reaction. And when we look at the reactions in which the nitrogen is retained, we will be looking at formation of azides, phenyl hydrazines and azo compounds. Some examples are the name reactions include Jab-Klingerman reaction and aryl coupling reactions. Welcome to the next session. In this session, we will be looking about diazonium salts. Let us have a brief overview about diazonium salts. The diazonium salts have a general formula Rn2 plus X minus. So, this is the general formula for diazonium compounds. And let us look at some of the reagents that are generally used for diazotization reaction. So, when we talk about diazotization reaction, in all the cases the starting material is going to be an amino compound. So, the amino compound is generally reacted with nitrous acid or HNO2. Again, the HNO2 is quite unstable. So, this is actually prepared by the reaction of NaNO2 and HCl. So, this is a standard reaction for the formation of nitrous acid, and we can also use metal nitrides. If the R group is an alkyl group, then what happens is those kind of diazonium compounds are highly unstable and they are very difficult to isolate. In most of the cases, they are never isolated. And because they are unstable, they readily decompose to carbocation, because when Rn2 plus X minus is present, so this N2 is lost as a nitrogen gas, and what we end up is basically R plus ion. R plus ion means this is nothing but a carbocation. So, the carbocation reactions you already know, it can undergo substitution reaction, it can nucleophilic substitution reaction, or it can also undergo elimination reaction. So, these are all the two major reactions of diazonium salts, basically the alkyl diazonium salts reactions. The next one is the R group can be a aryl unit. When we talk about the R group is an aryl unit, these diazonium compounds are relatively more stable than the alkyl diazonium salts, but still they are not highly stable. It is possible to isolate these compounds at low temperatures. So, the aryl diazonium salts are stable at a low temperature, few of them are stable at low temperature. And these diazonium compounds are basically, diazonium salts are basically synthetically versatile intermediate. They are the starting point for the preparation of many aromatic compounds, dyes, drugs, etc. So, in this session we will be looking at what are the various reactions of diazonium salts and how they are actually used in various synthetic preparations. So, let us look at diazonium salts structure and other thing. As we mentioned, they have a general formula Rn2 plus X minus. So, and we always get confused between two or three different types of compound. One is called the azo compounds. They also have N2 unit, and we also have diazo compounds which is also having N2 unit. So, that means there are three different compounds which have a common N2 unit. One is a diazonium salt which is having N2 plus unit, and azo compounds having N double bond N or N2 unit here again. and diazo compounds are having N2. So, all these are 3 different type of compounds. The general structure of diazo compounds, if you look at, as I have mentioned in the previous slide, the aryl diazonium salts are comparatively stable with respect when we compare it with the alkyl diazonium salt. So, here we have an example of a aryl unit, that means benzene unit is present here with the diazonium salt. So, this can undergo various resonance structures. So, the nitrogen is electronegative, since we have a that is a positive charge on the nitrogen atom, which is little less stable. So, the pi electrons from the aromatic system actually moves towards the external nitrogen. So, we have a double bond between carbon and nitrogen, and simultaneously one of the bonded electron is shifted towards the nitrogen. So, the nitrogen generates a negative charge. So, the first nitrogen still has a positive charge even though it has a double bond, and the aromatic ring also develops a positive charge. So, we have a carbocation. Now, as you know, there is a resonance stabilization of the other pi bonds within this particular benzene ring. So, we have a CH carbon, that is a carbocation present at the first in the ortho position, then in the para position, then in the ortho position. So, all the 3 carbocations are formed by the resonance, and once it is there, the negative charge on this nitrogen is now being shifted towards the internal nitrogen. So, we get a very similar structures to the starting material, that is whatever is given here. And in this particular case, because there is 3 bonds between nitrogen and both the nitrogen atoms. So, one of the bond is now shifted towards the positive nitrogen atom. So, the outside nitrogen is now having a positive charge. So, these are all the various resonance structures. If you look at the internal nitrogen is having a positive charge in one of the resonance structures, and the external nitrogen atom is having a positive charge in another resonance structures. So, that is the reason we say the positive charge may remain on either of the nitrogens depending on the various resonance structures. So, these are all the various resonance structures that are possible for the diazonium salt, due to which these diazonium salts are comparatively more stable when we compare it with the alkyl diazonium salts. In the case of alkyl diazonium salts, there is no resonance stabilization as we can see in the case of aromatic system. So, if we continue with the structure of the diazonium salts, even though we wrote various resonance structures, people were not very clear like how the compounds are actually connected. That means they took a simple salt, that is the benzene diazonium salts, and they were trying to figure out what is the actual structure of the benzene diazonium salts and where the aryl nitrogen is connected to the aryl unit is connected to the nitrogen. So, there were various structures proposed for this compound. Grice's proposed that the 2 nitrogens are actually connected to 2 carbons of the aromatic ring. So, this is one type of structure he had proposed, in which then there is a double bond between nitrogen and nitrogen, and this is a structure he had actually proposed for the benzene diazonium salt. Then Kekulé had actually proposed where there is only one nitrogen attached to the aromatic unit, that is one carbon and one nitrogen are the only 2 things which are connected to each other. So, this is how he had given the structure for Kekulé, and why he gave this structure was actually this particular diazonium salt can be converted to other derivatives, like when the X can be hydroxy unit or halogen or other different substituents, and the diazonium salt can be directly converted to these kind of compounds. So, this is possible only if there is a single bond or only one nitrogen is connected to the aromatic ring. So, in the case of 2 carbons attached to 2 nitrogen, these kind of products cannot be formed. So, that is the reason Kekulé suggested that there is only one bond or one nitrogen is connected to the aromatic ring. So, this is how he gave the structure for benzene diazonium salt. And of course, Bloomstrand had actually went further and studied few other characteristics of these kind of compounds. So, what he found out was based on the electrical conductivity of these diazonium salts, he identified that there are two ions present in the system. So, that is the reason we say, when we say diazonium salts, there is one ion, that is N plus is present, and there is also another ion Cl minus. So, there are two ionic units are present which are studied which are found using the electrical conductivity studies. So, that ruled out this particular structure, dimeric structure is ruled out, and then diazonium compounds are unstable, that people had actually found out, and that is the reason when they are formed in the reaction medium itself, they undergo reaction with the expulsion of nitrogen gas to give the corresponding aryl substituted units. So, that means diazonium compounds are unstable, so that people are aware of, and azo compounds are more stable. So, that means azo compounds are going to be different than the diazonium salt. So, that people found out using experimental evidences, and also they had shown that IR showed a triple bond character, that is diazonium salt is actually having a triple bond structure as shown here. So, there is a triple bond present, this is confirmed by IR studies. So, all these evidences actually point to the form to the structure of benzene diazonium salt as shown here. So, the resonance structure actually given here contains there is a bond between nitrogen and the halogen atom. Of course, here we can write the nitrogen is having a positive charge and the chlorine is having a negative charge. So, this is how we say, if we write this structure without a charge, then we cannot explain the electrical conductivity. So, that means even though this is the correct structure for writing benzene diazonium salt, what we have to actually give is a charge on nitrogen and the chlorine, which clearly tells that there are two ions present in this particular system. So, that is the reason this is the most acceptable structure for the benzene diazonium chloride. Now, people went further to study about the structure. They have taken the diazoiate structures where there are possible structural and geometric isomers are possible. When we say there is a double bond, of course, there are going to be geometrical isomerism possible. But when we talk about triple bond, there is hardly we can say any geometric isomerism. So, there is a difference between a double bonded structure and a triple bonded structure. Of course, in the resonance structures what we have seen earlier, let me go back to some of the resonance structures what we have seen. So, here we have there are more of nitrogen nitrogen double bond is present, also nitrogen nitrogen triple bond is present. So, in other words, what we can say is there are various resonance contributors which are having triple bond. So, this is one of the reason the IR structure actually showed there are more triple bond character for these diazonium salts. So, the other one is we can have two isomers, one is a N isomer, normal isomers, another one is called the iso isomer. So, that means various different scientists had given like one Penchman had proposed that these diazoiate compounds are having normal and iso structures. So, we will look at what are the normal and iso structures in the soon, and Hans had suggested these compounds are having a cis-trans form. That means cis-trans form is mainly for the geometric isomerism. So, how do they actually show there are different types of structure is basically the N-diazoacetate is the salt of diazo hydroxide. So, this is the diazo hydroxide structure. So, here there is a nitrogen oxygen bond that is formed in this particular system, and we have the isodiazoacetate. So, this is in this particular case there is a nitrogen nitrogen bond, and then basically oxygen is attached to one of the nitrogen, but here we have the hydroxy unit attached to the nitrogen. So, these are all the two different ways they have said the possible structures for the diazonium salt. And there is also another form where we have the cis or trans form or syn or anti form. In this case, there is a double bond between nitrogen and nitrogen. So, the aromatic unit and the other salt unit are present on the same side, and in other case they are present in the opposite side. So, these are all the two forms which are possible because of the nitrogen double bond. So, these are given by Hans, and he said this is a syn anti form or a cis trans form. And he also found out that the cis form is produced in a weakly alkaline solution, and it is relatively unstable or less stable. Because it is less stable, this is more reactive. So, this is one of the form between the cis and trans form. The cis form reacts much faster because it is less stable, and the trans form is produced in a strong alkaline medium. So, under these conditions, the trans isomer which is formed is more stable. Since it is more stable, it is less reactive. So, these are all the ways by which Hans had proposed that these kind of diazoiate compounds are having cis and trans are the geometric isomeric structures. So, people can equate the syn structure to the N or the normal diazoiate form. So, this is represented by aromatic unit attached to the nitrogen. There is a double bonded nitrogen between two nitrogens, and then the nitrogen oxygen bond is present. The M is the metal. In the previous case, if it is a simple diazoiate, there is a hydrogen atom present here. So, people had proposed that these kind of structures are possible for the normal diazoiate, and these type of compounds generally undergo base hydrolysis to give diazo hydroxide and diazonium hydroxide. So, there are two types of compounds. So, we are talking about the syn or the a normal one. This is normal diazoiate. So, this normal diazoiate have a nitrogen oxygen hydrogen bond. So, this bond on treatment with a strong base under basic conditions produces a hydroxy derivative. That means it is hydrolyzed to give the hydroxide anion and the diazonium salt. So, on the other hand, when we took the anti or the isodiazoiate, which is represented by the NO minus and M plus formula, because basically here we have the NO as a single unit, and this one undergoes hydrolysis to give N diazoiate and nitrosoamine as the product. So, the N nitrosoamine is formed as one of the product. So, that is the unique nature or the difference between the syn and the anti form. The syn form gives the diazonium salt and the hydroxides, whereas the anti form gives the N nitrosoamine structure. So, how do the people confirm that which is the correct structure for the diazonium salt? So, they went to other substituents, they prepared the diazosulfonates. So, the diazosulfonates, when we talk about X, is the sulfonate unit. So, we have different types of isomers. One is the structural isomers, that means N and iso structures, that is one type of isomer. Another one is a syn or anti isomer, which is the geometric isomer. So, there are evidences in favor of structural isomers. So, when this diazonium salt, we really do not know what is the actual structure, whether it is belonging to the syn anti structures or the structural N and iso structures, we do not know right now. So, we are going to identify which is the correct structure. So, for that, when we take the coupling reactions, there is a difference between, in one of the case we have the sulfite unit. So, when we have the sulfite unit, that can liberate nitrogen very readily when treated with copper sulfate. So, that tells that, and of course, there is also another major difference between the reactivity. One of the isomer we do not know, we have isomer A, we have isomer B. So, out of this, one isomer is highly reactive, another isomer is less reactive. So, this is the only thing what we actually find out through the experiments. Now we have to identify what is the actual structure of A and what is the actual structure of B. So for that, what we are going to do is we are going to study the various reaction and to accept or reject what is the probable structures. So in one case, the isomer A is more reactive, isomer B is less reactive. So how we can actually make this difference is there should be different type of bonding. So in the case of the isomer, first we have a nitrogen sulfur bond. Okay, so this is one type of bond. In the other isomer, we have a nitrogen oxygen bond. So that means there are two types of bond. So their reactivity is obviously going to be different. So that way we can actually say these two are the probable structures for the diazonium salts. And if we take the sulfite structure, when we treat the sulfite structure with the copper sulfate, the nitrogen gas is liberated readily. So that means because this NS bond is a weak bond, so it is broken very readily, and that's the reason we get the nitrogen gas evolution very quickly. So one of the isomer is more reactive. So this is can be the cis isomer or the normal isomer, which actually are readily loses nitrogen, and B is less reactive. This is more reactive. So this compound does not liberate nitrogen very readily. So that means this structure does not liberate nitrogen. So this may be the iso structure, and this may be the normal structures, like that people had proposed. That is one set. And in the other case, when we talk about cis and trans, so what are the reactions which are in favor of cis and trans structure? So these two compounds react with phenol directly. So that means when we have the NO bond, this particular iso salt is less reactive. So that means it cannot react with phenol. So the reaction with phenol cannot be explained by this structure. So this is ruled out now. I mean, it's going to be very difficult to say there is a NO bond which can be broken easily to when it is reacted with phenol. The second one is oxidation by iodine. So this compound can undergo oxidation very readily, whereas this isomer cannot be oxidized very readily, whereas cis and trans can be oxidized very readily, because in both the cases we have the same nitrogen sulfur bond. So the nitrogen sulfur bond is very readily undergoes various reactions, which is also seen in the case of normal isomers. So all these things point to the fact that there is a nitrogen sulfur bond directly, and that is responsible for its reactivity. And of course reaction with the mineral acid liberates sulfur dioxide gas. So that means unless we have the SO3 unit present, the sulfur dioxide formation is not possible. So because it is basically S double bond O, S double bond O, and OK, this is the structure. So this SO2 can be easily lost, that is possible. So here we have the nitrogen aromatic unit. So SO2 loss is very easily possible when we have this kind of structure. So that is the reason all the compounds has to have the SO3 unit. So that very clearly tells that this iso structure is not possible. And again, these two compounds have similar absorption spectra. So when they have similar absorption spectra, then obviously they have to have the similar structure. It may be cis trans isomer, that is perfectly fine, but they cannot have two different functional groups. Here NS bond is there, here NO bond is there. So because of the change in the bonding, we cannot have the similar absorption spectra. So all these evidences point to the fact that there is a cis or trans isomers possible, or syn or anti structure is possible for diazonium salts. And we also have another set of experimental evidences in the case of diazocyanides. So this is even added more weightage to the structure, which is actually the cis or trans structure. So we call this as a syn structure, this is the anti structure. So what are the evidences which favor this kind of structure is basically this reacts with 2-naphthol. So that is in the previous case also we had seen phenol reactivity. So when we look at the reactions of diazo compounds, we will see how the reaction actually proceeds. And the copper powder actually decomposition leads to aryl cyanide. So these two reactions prove that syn but not anti structure is possible. So they are talking about only one structure, but of course they are still restricting to this particular structure, which is more reactive or highly reactive. And syn and anti both are possible using these three experimental evidences. That means both react with mineral acid to give the same amide or acid. So in other words, when we have the cyanide actually undergoes hydrolysis to give the amide, and this amide further undergoes hydrolysis to give the acid. So we get the same acid and amide on hydrolysis, which clearly tells that we have to have syn or anti structure only. We cannot have anything different from that. And then by looking at the dipole moment, refractive index, UV absorption spectra, all these things point to the fact that there are two types of isomers, that means syn and anti are present because of the extension of conjugation, and they also have same vibrational spectra. So these are all the evidences which prove that the compound is formed present in the syn and anti form. So with that we can conclude that aromatic diazonium salts can have either syn or anti form, and the syn form is more reactive, and since it is more reactive, this is less stable. We can also say it is less stable, that is why it is more reactive. So the reactivity and stability are inversely proportional. So this is less stable. So that way the different reactivity of the diazonium salts can be explained very readily. So these are all the two examples where the syn react faster than the anti. So let us look at the various methods of preparation. The first one is the nitrous acid can be used to convert the aromatic compound, especially aromatic normal or the simple aromatic hydrogen with simple hydrogen, there is no other substituent. So can be converted with the nitrous acid in the presence of HX to give the aromatic diazonium salts. So for this is generally applicable for activated aromatic systems. For the deactivated aromatic systems, we have to use nitrosyl sulfuric acid and mercuric sulfate can be used. So these are all the different methods by which the aromatic simple aromatic compounds can be converted to diazonium salts. So how the reaction actually proceeds is explained in this particular scheme. So the nitrous acid can be written as HONO. So this under acidic condition, because we are carrying out the reaction under acidic conditions. Under acidic condition, protonation takes place on this particular oxygen. So we have the H2O plus ion that is formed in this reaction, and the H2O plus ion, which is a very good leaving group, can be easily lost. That leads to the formation of nitronium ion. So this NO plus ion formation is a very crucial fact, and this is the electrophile which is involved in all these reactions, and this when reacted with halide ion forms NOx, and when aromatic amino compounds are treated with this NOx compound, we end up with ARNHNO, and this leads to the other products. And two molecules of HNO2 also can form N2O3 and water molecule is lost. So this N2O3 can again react with ARNH2 to give this particular intermediate. And of course this nitronium ion can also directly react with the aromatic amino compounds, but that reaction is going to be slow. So these are all the various steps by which the aromatic diazonium salts can be produced. And when there is a electron withdrawing group is actually present, that especially in the para position, that reduces the nucleophilicity of the amino nitrogen. So if you look at the aromatic system, so there is a lone pair on nitrogen, but we have a electron withdrawing group. So when the electron withdrawing group is present, this actually pulls the electron towards this aromatic ring, and then this comes here, and this double bond comes towards the electron withdrawing group. So that is the reason the lone pair of electron available on this nitrogen becomes less. In other words, this becomes less nucleophilic in nature. When it is less nucleophilic in nature, this cannot actually react with the nitronium ion, which is the electrophile. So, that is the reason whenever there is a electron withdrawing group present in the para position, that reduces the reactivity of the nitro compound. So, this is one of the things we have to remember all the time. In other words, the rate of diazotization becomes very slow. So, let us look at other reactions of diazonium salts. So, the first one what we are going to focus is on the loss of nitrogen atom. So, there are various reactions which lead to different type of product. The first one is the replacement by hydroxyl unit. So, the diazonium salts when treated with aqueous conditions leads to hydroxy ion, that means phenols can be formed from the benzene diazonium salt when treated with aqueous conditions, especially water. In the acidic condition, in the presence of an acid, leads to the formation of phenols. And the next one is replacement by hydrogen. So, H3PO2 reaction with diazonium salts leads to the loss of nitrogen atom, and hydrogen replaces this one. So, we simply get the substitution of the N2 group. And the next one is the replacement by halogen atom. We have different types of reaction. We have Sandmeyer reaction, Gattermann reaction, and Ball-Steelman reaction. Depending on what is the reagent we use, we have different type of products. The Ball-Steelman reaction is for the fluoro derivative. So, we can use copper chloride and HCl, copper bromide and HBr, or sodium nitrate, HX and HBF4. These are all the various conditions by which we can prepare chloro, bromo or fluoro derivatives. And the replacement by cyano group can be carried out using copper cyanide, and replacement by the nitro group is also possible. So, that leads to the nitro substituted aromatic systems. And finally, we can also replace the diazonium salt by the aryl unit. So, Gomberg reaction and Meerwin reactions are examples of that. We will look at all these reactions in the later part currently. So, first one is the replacement by hydroxyl. So, here the diazonium salt is treated with water. As we mentioned, this is under acidic conditions. So, under acidic conditions, either boiling with water or steam distillation of the diazonium salt gives the corresponding hydroxy derivative. So, basically the phenolic derivatives are formed. And this reaction actually proceeds via SN1 mechanism, because as we have mentioned, this leads to the formation of phenyl cation. So, that is one of the very rare cases where the aromatic system is having a positive charge. So, we have a phenyl cation which is formed in this particular system, because nitrogen is lost as nitrogen gas, and this leads to the formation of phenyl cation, and this phenyl cation undergoes SN1 type reaction to give the phenolic derivative. And of course, if the reaction is not carried out carefully, we end up with a tar formation. That means lot of black materials will be formed in this particular reaction. This happens when we are running the reaction under either weakly acidic conditions or moderately hot, not boiling water. So, to get the hydroxy derivative formation, the reaction has to be carried out with a strong acid. A very strong acid is very essential, and also the reaction should be carried out with steam or boiling water. The next one is the replacement by hydrogen atom. So, here we look at deamination reaction. So, the amino compound is converted to the corresponding diazonium salt. So, this diazonium salts on treatment with ethanol and zinc gives the corresponding aromatic compounds. So, this is a very important reaction in the synthesis of various derivatives. So, this reaction is useful when a direct formation of particular substituted aromatic compounds are very difficult. So, once we look at some of the examples, we will know what are all the examples we can actually prepare using this particular reaction. So, some of the reagents that are used in the reactions, that means mainly from the amines, are nitrous acid and hypophosphorus acid. So, this is the first one, which simply replaces the diazonium salts with the hydrogen atom. We can also use a combination of sodium nitrate and sulfuric acid. So this is a combination which leads to the formation of the diazonium salts, and when the reaction is carried out in ethanol, that replaces the diazonium salts with the hydrogen. And sodium nitrate and HbF4 followed by zinc and ethanol treatment also gives the, so this is the example given here. The amino compound is converted to the borofluoride salt, and this diazonium borofluoride salt is treated with ethanol and zinc, gives the corresponding aromatic compounds. And especially this reaction is useful for the preparation of polyhalogenated arenes, meta-substituted arenes, and these are very important compounds which cannot be prepared by any other method, can be prepared using this diazonium salt method. So let us look at some of the examples of this particular reaction, that is the deamination reaction. So when we have if you want to prepare metabromotoluene, it's very difficult to prepare the metabromotoluene because this methyl group is orthopara directing. This bromo group is also orthopara directing. So when we have two orthopara directing, there is no way we can prepare a meta substituted these two orthopara directing groups to be present in the meta position. So this is one of the difficulty we will be facing. Of course, in this particular reaction, if you look at the meta-nitrotoluene, we can actually think of this is a meta-directing group, and this is a orthopara-directing group. So we can actually think this meta-directing group can actually introduce the methyl group into the meta positions. But unfortunately, nitrobenzene is so highly unreactive and deactivating, so we cannot employ Friedel-Crafts reaction to introduce the methyl group. So this rules out like when two orthopara substituted groups are present in the meta position, that is not possible to be prepared easily. Similarly, when there is a meta-directing group or deactivating group, it is also not possible to prepare the corresponding products as shown here. So these reactions can be easily prepared using the diazonium salt. So how do we prepare this one? So in this particular case, we have a starting material is the amino derivative. So this amino derivative, this compound can easily be prepared. So once we introduce the bromine, then we can actually convert this amino group to the diazonium salt, and this diazonium salts can be replaced by the hydrogen atom by treatment with ethanol and copper. So here we get around 60% of the yield. So this directly gives the required metabromotoluene product. Similarly, when we start with this amino derivative, so it is also, we can follow the same step of reactions to prepare around 70% of the meta-nitrotoluene. So this way it is possible to prepare the compounds which are very difficult to prepare by other methods. Similarly, we have another compound, the tribromobenzene preparation, symmetrical tribromobenzene, very difficult. So this can be easily prepared from the amino derivative, because here if you look at, these are in the meta position, these two, and again this is two meta position. So the bromine in the meta position is not possible, like if you say 1, 2, 3, 4, 5. So 1, 3, 5. Substitution is not possible by the normal method of preparation. So that can be easily prepared if you start with the amino compound. So aniline can be easily tribrominated to get this particular product. Here we have the ortho substitution, here also we have the ortho, here we have the para. So in other words, the bromination can actually give the required product in large quantities and in as a single product. And the amino group can be easily removed by conversion to the diazonium salt followed by treatment with ethanol. So this is one way of preparing this tribromo derivative, which is the meta substituted tribromo benzene, can be easily prepared. The another one is the meta dichlorobenzene. So this is also another difficult compound which cannot be synthesized easily. So that can be prepared using corresponding amino derivative. So here again, if you look at, this is in the ortho position, this is chlorine is in the para position. So this ortho and para chloro derivative can be easily prepared from the aniline, corresponding aniline, and then removal of this amino group, that is the deamination, leads to the corresponding meta dichlorobenzene. So, of course, there are few limitations for this reaction. So, the major limitation is when the aryl diazonium salts are treated with alcohols, ethers are also formed along with the corresponding deaminated product, and this formation of ether basically depends on the structure of the aryl diazonium salts and the nature of the alcohol. So, these are all the two crucial factors which decide what is the product. In fact, if we take the benzene diazonium salts and treat with ethanol, we get 61% of the corresponding ether and we get only 5% of the corresponding aromatic compound, that is the benzene. So, this reaction has to be carried out very carefully. We have to choose the right diazonium salt and the right alcohol to make this reaction effective to get only the deaminated product. Otherwise, we end up with the ether which is the unwanted side product. And of course, when a negative group is present in the ortho position, the reaction in ethanol produces arenes, whereas the reaction with methanol produces ether. So, again choice of solvent is very important, as we mentioned here. The nature of alcohol also plays a vital role in what is the product that is formed, whether it is a ether or whether it is a normal aromatic compound formed by the deamination reaction. The next one is replacement by halogen. So, here let us look at the Sandmeyer reaction. So, treatment of cuprous halide, that is in the presence of a HX acid, the diazonium salt is converted to the halo derivative. So, the amino compound is converted to the diazonium salt in the first step, and the treatment with cuprous halide and HCl produces the corresponding halo derivative. And here there is a halogen attached to the metal. So, this halogen is the one which is actually attached to the product, the diazonium product. So, that means not the HCl is not coming from the solvent or the acid which is used, but the chlorine is coming from the metal salt. So, that is identified using various experiments, and it was confirmed that the replacement of the halogen comes from the metal salt. And similarly, when we take another substitution here, the toluidine is converted to the corresponding diazo salt, followed by treatment with the cuprous bromide and HBr gives the para-bromotoluene. So, this is again a place where the amino group is replaced by the halogen atom. So, this is the Sandmeyer reaction. So, here the important thing what you have to remember is we are using cuprous halide as the salt. And when we go to the Gattermann reaction, the Gattermann reaction is also very similar to the previous one what we have seen. The only difference is here we are using copper powder at room temperature. We are not using a cuprous salt, but we are using copper powder. So, here in this particular case, the amino compound is converted to the diazo derivative by treatment with sodium nitrate and HBr. So, this is the standard combination for the diacetyzation reaction. This on treatment with the copper produces the replacement of the diazonium group by the halogen takes place. So, we end up with the orthobromotoluene. So, the next one is a Ball-Streelman reaction. So, in this Ball-Streelman reaction, we are using borofluoric acid is actually used as an important intermediate in this reaction. So, that means the amino compound is converted to the corresponding diazonium salt first, and this was again treated with HBF4 to give the corresponding diazonium borofluorate salt. So, this is the most important one. This borofluorate on heating produces the corresponding fluoro derivative, and we can also use the same reaction as sodium nitrate HF combination produces the corresponding fluorodiazonium salt. So, the fluorodiazonium salt can also be converted to the fluoro derivative directly. So, these are all the two methods by which we can actually carry out this reaction. In this particular case, the diazonium borofluoride salt precipitates out from the reaction mixture. So, it is very easy to isolate this particular diazonium salt, and as we mentioned, the aromatic diazonium salts are quite stable. So, once we filter it out at low temperature, we can simply heat this and the nitrogen is lost as a nitrogen gas, and we end up with the fluoro derivative. So we can also carry out the same reaction by running the diazotization at a low temperature using NaNO2HF combination. So this is allowed to stand, also liberates nitrogen, and then we end up with the corresponding fluoroderivative. The next one is replacement by iodine. So here by boiling this diazonium salt with potassium iodide produces the corresponding iodo derivative. So this is a simple substitution reaction. The nitrogen is lost and the corresponding group is being replaced by the iodine atom. And we can also carry out the same reaction as replacement by cyanide ion also. So basically treating the solution of the diazonium salt with the aqueous KCN in the presence of copper cyanide. So this combination, or we can simply use KCN and copper. So either of these conditions produces the corresponding cyano derivatives. The next one is replacement by the nitro group. So diazonium salts are treated with sodium nitrate and HBF4 actually produces the corresponding diazonium fluoroborate salt. This on treatment with another additional equivalent of sodium nitrate and copper produces the nitro derivative. So this is one way of preparing the nitro compound. And another way is like the diazonium chlorides or the diazonium halides can be treated with one equivalent of sodium nitrate in the presence of copper oxide. So in both the cases what we are going to use is like the cuprous oxide can be used or the copper salt can be used, and we have to use one additional equivalent of sodium nitrate after the diazonium salt is formed. So this is the most important thing in this particular case, because the reaction itself uses sodium nitrate to form the diazonium salts. So once the diazonium salt is formed, then additional one equivalent of sodium nitrate with the copper is mixed to give the corresponding nitro derivative. The next one is replacement by nitro group. One additional advantage for this reaction is basically it's very difficult to prepare polynitro compounds. So in this particular case, especially since we know the nitro group is actually meta-directing, so we are actually preparing a para-substituted nitro derivatives, which are generally not possible by normal or the conventional methods. So this amino group converted to diazonium salt and the displacement of diazonium salt with the nitro group is the best method to prepare the this para-dinitro derivatives. There is also other methods by which the nitro group can be introduced into the diazonium salt. So the diazonium salts, when treated with cobalty nitrate. So this cobalty nitrate is formed by the reaction of disodium, the diazonium salt with the sodium cobalty nitrate, and this was further treated with the sodium nitrate. So this is the most important thing. Every time whenever we prepare the diazonium salt, the next step is the treatment with the sodium nitrate to give the nitro product. So here copper oxide and cuprous oxide and copper sulfate gives the maximum yield. So we can get a higher yield of this particular compound, and similarly we can also convert a diazonium compound, diazonium salt, to the nitro derivative by treatment with the sodium nitrate and sodium bicarbonate. So this reaction also gives high yield of the nitro derivative. So these are all the couple of methods by which a nitro group can be introduced to the aromatic system. The next one is replacement by aryl group. So the diazonium salts are treated with the copper powder and ethanol produces the corresponding biphenyl derivative. Of course, this reaction does not give very high yield. As you know, earlier also we have seen copper and ethanol condition generally gives the replacement of this diazonium salt with hydrogen also. A simple replacement also is possible because earlier we have seen this particular reaction. So this is actually a competitive reaction where we can also get benzene and biphenyl. So that is the reason here it is shown that the reaction gives only 25% of the yield, or we get only a very poor yield of this biphenyl derivatives. So people went with another modification to this aryl coupling reaction. So here in the Gomberg reaction, the diazonium salts is treated with the aromatic system in the presence of a base. Sodium hydroxide is used as a base. So here we get the diaryl derivative, and in most of the cases the substitution takes place at the para position or the place where the diazonium salt is actually present. So, simple reaction with the diazonium salt and the nitrobenzene produces the para substituted one. So, this is how generally the reaction proceeds. In most of the cases, either the ortho substitution takes place or the para substitution takes place, and preferably since the aromatic ring is very bulky, the para substitution is very readily taking place. So, as ortho and para are possible, and in most of the cases para is formed as the major product because of the bulkiness of the groups that are present in the aromatic system. So, the next one is the Meerwin reaction. So, this is a little bit different reaction. Here again this is a aromatic coupling reaction. So, in this reaction activated methylene compounds, basically they are electron poor alkenes, and the diazonium salts are reacted. We have a diazonium salts, we have a electron withdrawing group on an alkene. So, these are called the activated ethylene compounds in the presence of a metal salt. Basically here we can use sodium acetate or other metal salt, produces the corresponding diaryl derivatives. And if we have other electron substitution, basically if the electron withdrawing groups are like carboxylic acid or various other groups are also possible, and if we have a carboxylic acid, what happens is the carboxylic acid is actually lost or the decarboxylation takes place, which leads to the conjugated alkene is formed as the final product. So, we have the benzene diazonium salt, here we have the cinnamic acid. So, these two react together to give stilbene, like a stilbene is given in this particular case. So, this reaction, the carboxylic acid group is completely lost. So, this is one of the example of forming the biaryl or the combination replacement of diazonium salt by the aryl substitution. The next one is a Schar reaction. So, in this reaction, rather than forming a biaryl type systems, what we are having is basically the cyclization actually takes place. We are actually forming another ring. So, this is an example of a ring closing process. So, we have to start with the suitably positioned amino derivatives. The starting material should have a suitably positioned the starting material should have a suitably positioned amino derivative, and this amino derivative can be converted to the corresponding diazonium salt, and this on treatment with copper 1 salt or copper cuprous oxide gives basically the phenanthrene type reaction or the cyclized derivative. So, the X can be CH double bond CH, it can be a aliphatic simple alkyl system, or it can be a heteroatom like oxygen, sulfur, nitrogen, etc., or it can also be a simple methylene unit. So, depending on various substituents on this X, we can actually get a different membered ring in this particular system, whether we may get 5-membered ring or it's a 6-membered ring, depending on this particular substitution on the X. So, this kind of reaction is called Schar reaction. So, in this one a cyclization takes place, that means there is a substitution of one of the aromatic ring to the corresponding diazonium salt. There are also other groups which can be used to displace diazonium salts. One is isothiocyanates. So, when we use thiocyanates, so the thiocyanates can be reacted with diazonium salt to give the corresponding derivatives. Isocyanates on treatment with the diazonium salts in the presence of a metal, that is copper, gives the corresponding isocyanate derivatives, and the sulfur derivatives also can be used to displace the diazonium salt. So, these are some of the examples given here, and aromatic diazonium salts can be converted to the corresponding ketones by the treatment with as shown here. So, oximes can be used in this particular reaction. So, the diazonium salt and the oximes react together to give the corresponding substituted ketone derivatives. The next one is reactions of diazonium salts in which the nitrogen is retained. So here the reactions what we will study are formation of acids, formation of phenyl hydrazines, and formation of azo compounds and aryl coupling reactions. So the first one is formation of acids. So the diazonium compounds when treated with bromine and HBr leads to the formation of perbromide. So the diazonium perbromide is formed. This on treatment with aqueous ammonia gives the corresponding acid. So this is one way in which the nitrogen is retained in the product. The previous reactions whatever we have seen, in all the cases the nitrogen is lost as a gas. In these kind of reactions what we are seeing currently, the nitrogen is retained. Of course, if we want to prepare this corresponding acid, phenyl acid, there is also another method where nitrosobenzene can also be treated with hydrozoic acid to give the phenyl acid. The next one is reduction to form the aryl hydrazines or anilines. So the amino compound can be converted to the corresponding diazonium salt. So this is we know the standard process. So once the diazo derivative is formed, when this is treated with Na2SO3 or SnCl2 and HCl. So these are all the two different reducing agents which can be used. Depending on the reducing agent used, we can end up with the corresponding phenyl hydrazine derivative. So the phenyl hydrazine derivative can be formed by the reduction of the corresponding diazo salt. And if we use some harsh reducing agents like zinc and HCl, what happens is this corresponding hydrazine compounds, aryl hydrazine compound can be further reduced to the corresponding anilines, that means amino derivatives. So one of the NH2 group is lost and we end up with the corresponding aniline derivative. So for this reaction to occur, we have to use some harsh reducing agents like zinc and HCl. The next one is coupling reactions of aromatic diazonium compound. So here the nitrogen on the diazonium salts has a positive charge. So we can say that is going to be the electrophilic site for that reaction. So its reaction with the aromatic system is very similar to aromatic electrophilic substitution reaction, we can say. So when we say ArN2 plus, the N2 plus is having a positive charge. So this is very similar to an electrophile attacking the aromatic system. So this diazonium reaction can also be termed or considered like aromatic electrophilic substitution reaction. So what type of substrates will undergo reaction when the aromatic system is activated? So they generally undergo this kind of aromatic electrophilic substitution reaction. So similar to that, when electron donating groups like phenols or aromatic amines are present, they undergo coupling reactions in alkaline conditions, or it may happen at neutral or even mildly acidic medium. So this leads to the formation of highly colored azo derivatives or the colored compounds. In the case of phenols and naphthols, the condensation takes place between the ring carbon and the diazonium nitrogen. So this is called a C coupling reaction. And in the case of amines, the initial condensation actually takes place between the side chain nitrogen and the diazonium nitrogen. So this is called N coupling. Of course, this undergoes a rearrangement to give the C coupling product as the final one. Let us look at some of the examples. So the first one is the condensation. What we talked about is the C coupling reaction. So here the diazonium salts is treated with the corresponding aromatic derivative. So here we have a NMe2 group which is attached to the aromatic system. So this is the amino derivative what we are talking about, and whenever we have the amino derivative, the reaction is carried out under acidic conditions. That leads to the azo compounds. This is different from the diazonium salt. So this is what we had seen in the beginning of this session. So the diazo compounds are different and azo compounds are different. So this azo compound is nothing but a di. So these are having extension of conjugation, and that leads to highly or bright colored substances, and these are used as dyes in various places. And all these cases we have a hydrogen which is highly labile, and in most of the cases the labile hydrogen is present in the para position. So the labile hydrogen compounds include, it can be a phenol, it can be a naphthol, it can be a primary, secondary or tertiary aromatic amines. So all these compounds make this hydrogen highly labile, and because of this reason the condensation or the C coupling takes place very readily, and in all these cases we end up with either ortho or para substituted product. So here in the first example we have the para substituted derivative, and in this compound also we have the, here we have the ortho group which is actually substituted here. We have the nitrogen group in the para position, so that's the reason this compound is called para red, and it is having the red dye. The color of this compound is red color, and this hydrogen which is in the ortho position to the naphthol hydroxy unit. So this is the hydrogen that is being replaced. So this is how the, here is the N double bond N compound. So this is, the nitrogen is retained in the final product. So this is an example of the reactions in which the diazo nitrogen is retained in the final product. The next one is Jaap-Klingerman reaction. So in this reaction, the previous cases we saw the active or the labile hydrogen is present in either phenols or naphthols or the amino compounds. So in this particular case, that Jaap-Klingerman reaction uses the labile hydrogen that is present in active methylene group. So we have an active methylene compound here which is having, here in this particular case we have two hydrogens which are active or the labile hydrogens. So these labile hydrogen can be actually the site of condensation. So here again there is a carbon and there is a carbon from this aromatic system. So the coupling happens between two carbon atoms. So that is why we call this reaction as a C coupling reaction. So what is the site? Here it is attached, it is the carbon to which this particular compound is attached and the diazonium salt is attached. So here in this particular case the reaction happens when we have the enolic form of the acetoacetic ester, and this particular compound undergoes condensation to give the coupling compound as shown here. So this is nothing but the acetoacetic ester. So the reaction happens in the presence of sodium hydroxide. So in the presence of sodium hydroxide the enolic form undergoes the reaction to give the CC coupling reaction. The next one is the N coupling reaction. So in this particular case the diazonium, the condensation happens between the diazonium salt and the corresponding labile compound. So here what happens is, instead of this particular hydrogen that is undergoing reaction, it is this nitrogen which actually undergoes the reaction with the diazonium salt. So we have a reaction occur as shown here, and this nitrogen is the one which actually reacts with the diazonium salts. So this is the one which leads to nitrogen coupling. So of course this compound is quite unstable, and this undergoes rearrangement to or it undergoes disproportionation to give this kind of two intermediates, and this intermediates again now this undergoes reaction with corresponding aromatic this carbon derivative, the other end of the carbon. So we end up with our azo compound as shown here. The amino group is in the para position. So this is the product which is generally obtained by the C coupling reactions, but of course in this particular case the reaction proceeds via the initial N coupling followed by rearrangement. And why the azo dyes are used for coloring? If you look at these compounds have extension of conjugation as we have seen earlier. So depending on the substituents and their position, the azo dyes have different colors and they have very bright colors. And basically azo dyes generally have multiple aromatic rings. So that means they are also insoluble in water and many other solvents. So they have bright colors, they are also insoluble in water and other solvent. So these are all the two major properties by which the dyes are generally used for coloring. And these dyes are used for coloring plastics, rubber, paints, etc. And of course many azo dyes are non-toxic, that's the reason they are used in textiles and our clothes. But there are certain type of dye compounds which are having amino groups are not good for, they are found to be toxic, so they are not generally used as coloring for the our dresses and clothes. Otherwise, they can be used in paints and other plastics, rubbers, etc. So, because of extension of conjugation, these azo compounds are brightly colored, and that's the reason they are generally used as a dyes. Let us recap in the summary what we have seen so far. We have studied about various methods of preparation of diazonium salts. Most of the reactions follow nitrous acid as the major diazotizing agent, and amino compounds are converted to the corresponding diazonium salts using treatment with nitrous acid, which was formed by the reaction of sodium nitrate and mineral acids. The next one is we studied about the reactions of diazonium salts. So, there are two major categories we have seen. One category where the diazonium group is replaced by hydroxyl unit, hydrogen, halogen, cyano, nitro or aryl groups. So, any one of the group replaces the diazonium salt that we have seen, and we have also studied about the name reactions like Sandmeyer reaction, Gattermann reaction, Balz-Schiemann reaction, Gomberg reaction and Mervin reaction. So, in most of the reactions, the catalyst is the one which is actually changing, and how the reaction actually proceeds we have seen. Then we have also studied about reactions where the nitrogen is retained, that is the diazo nitrogen is retained in the final product. Some of the product formation include acid formation, phenyl hydrazine formation and azo compound preparation. We also have studied about Japp-Klingerman reaction and aryl coupling reactions. In the aryl coupling reactions, we studied about both the C coupling and the N coupling reactions. We also saw the use of dyes in the industry. With that, we conclude this particular session. Thank you.